We are starting chapter 2 today, which is all about functions. So, since it's lesson 1, this is where we're learning the fundamentals about our functions. So if you're not understanding something, ask me now before we get too deep into it. A function is any rule that assigns exactly one output value, commonly our y values, for each input values, our x values. These rules can be expressed in different ways, the most common being equations, graphs, and tables of values. We call the input variable independent and our output variable dependent.
Can we take a picture of this?
I'm actually uploading this lesson to a YouTube channel, maybe. I'm going to try to see if I can do that. But yeah, if you want to take a picture, just make sure I'm not in it. Relations and functions are commonly spoken about together. So a relation is a relationship between sets of information. Most commonly we'll see it as an ordered pair. So we know that when we are speaking about our domain, we're talking about the set of all x values, or commonly our independent variables. Then our range is the set of all y values, or our dependent variables. So our range is dependent upon our domain. A function is a specific type of relation. In order for a relation to be a function, there must be only and exactly one y that corresponds to a given x. Basically, this means that elements of the domain never repeat. So in order for something to be considered a function, our x values cannot repeat. Does anyone still need this? Well, we want to know, is it a function? One way to test if a relation is a function is by using the vertical line test. I never get this right every year, 4 years. The vertical line test is straight up and down. Okay, vertical lines are up and down, horizontal lines are left and right. Vertical lines are up and down, we're all doing it. Vertical lines are up and down, arms extended, nobody's got broken arms, out and about. And then horizontal lines are left and right, like the horizon and sunsets. Vertical, horizontal, vertical. You guys are like blessing me. Horizontal. Okay. This test can be used when the relation is graphed. The vertical line test states that if a vertical line is drawn anywhere on the graph so that it hits the graph in more than one spot, then the graph is not a function, because that would say that we had more than one output for our x value. So we're going to try our most common parabola. F of x is x squared. We want to know, is this a function? So we have our parabola here, and we're drawing our vertical line test. And we sometimes want to draw a couple, because sometimes the width of our graph is going to be different in different spots. So I have these two vertical lines drawn on, and I want to circle where they intersect. So on this line on the left, it only hits my function in one point, right there. So far, so good. Over here, again, it only hits it in one place. So because there's not more than one hole on each line, is this a function, yes or no? Yes. At every x value, we have a different y value. Okay, that's because we only had one hole on either of those lines. For letter B, we rotated our parabola onto its side. We want to see if this new parabola is a function. So on the line to the left, we intersect here, we intersect here. Our line to the right, we hit the function here, we hit the function here. Would we consider this a function, Frank? No. Why not? Right, at this x value, let's say this is x equals 4, my y equals 1, and my y equals negative 1. So because at this x value, at x equals 4, I have two different output values, it does not make this a function. So again, this is our vertical line test, and we use this when they give us a graph. Determine if each of the following graphs are functions. So we have these 6 different maybe functions, maybe not. I want you guys to apply the vertical line test and tell me if they're a function or if they're not a function.
The two lines you draw on the two sides like the y-axis?
What happened?
The two lines you draw on the two sides of the y-axis?
Yeah, I mean, I would just try to draw it and spot where the function looks different. There's like no really right or wrong place where to place them. You can draw 31.
When you're doing the dog, that has to be the same side as the graph, right?
No.
Oh, it can be
Yeah.
something else. Okay.
It's weird. Some of us aren't drawing lines, and it's so crazy because I think I said we had to draw the line. I just don't know why we're so against following the rules. Hey, Coach.
How are you?
It's Friday, so I'm better. How are you?
Okay.
I'm ready to go home. Okay, so I mean, it looks like craziness on, looks like the matrix is something on the board right now. But this is what it should look like. And then the extra step we're taking is drawing where they intersect, where our holes are. So for letter C, at this line I hit it once, hit it once, hit it once. So is C a function? Letter D, I've got multiple holes on my lines.
No.
Not a function. Okay, or a simple no. Letter E, P's good. Oh, well, there's only one hole here. 3 holes, 1 hole here. What do we think?
No.
No, good. Letter F, 1 hole, 1 hole, 1 hole.
Yes.
Good. Letter E, I hit there, I hit there, I hit there. Good. Oh, that was G, sorry. And letter H.
No.
Thanks, Ron. How do we feel about our horizontal line test? Who got all 6 correct? Yay! One of the following graphs shows a relationship where y is a function of x and 1 does not. Draw the vertical line whose equation is x equals 3 on both graphs. Give all output values for each graph at an input of 3. So we're adding on an extra idea where we have the functions graph for us, but we're going to pull the information out and organize it in a table. Because that's going to be another way that we're going to see our functions represented to us. So they walked us through this and they told us the first thing to do is draw in, the vertical line of x equals 3 on both graphs. Which direction are my vertical lines again? What happened to your 3 arms? What happened? Thank you. Guys, you're going to forget, and you're going to remember this. So x equals 3, if this is 0, 1, 2, 3, I'm drawing my vertical line here. X equals 3. They told us to do that for both functions, so I'm going to count x equals 3 on my parabola as well. 1, 2, 3. Always labeling x equals 3.
Does that have to be dashed, or can it just be a straight line?
We like to do it dash, but I'm not going to I don't have the time or energy this year to get hung up on that. So we did our first step. Step B says, give all output values for each graph at an input of 3. Is relationship A a function? Why not? Where does it intersect?
It intersects on 3, 5.
Okay, check again.
4.
3, 4. And where else does he intersect? Frank?
3 negative.
And then how about relationship B? Would we say he is or is not a function? What is happening with that? Relationship B.
It is a function.
Why?
Because only intersect at one point, which is negative 3 to negative 3.
Not negative 3, negative 3. Frank?
Oh,
Negative 3.
No.
Negative.
No. Okay, so x value hasn't changed.
oh, 3 to negative
3,
and negative 2.
negative 2. So now, on top of having our graphs, we're able to see in a table. Would we be able to quickly identify if we saw relationship A given to us as x, y, when x is 3, y is 4, and when x is 3, y is negative 4. And then for relationship B, if we saw when x is 3, y is negative 2, can you easily identify between those two tables which one is and is not a function? So which one is a function?
First one. I mean, B.
B. Relationship B is a function. Why?
This one has 1 point of intercept. I mean, 1 point where the line intersects the circle.
What were you going to say?
I was going to say
Well, so relationship B is a function because it only has
1x.
one output for our x value. Okay, that's what's important. They can have multiple x's, but they can only have one output per x. Anyone still copying that down? All right. The graph of the function y equals x squared minus 4x plus 1 is shown below. We're going to answer 4 different parts. What is this function's y-intercept? Between what two consecutive integers does the larger x-intercept lie? Then we're going to draw our horizontal line of y equals negative 2 on the graph. And then we're going to solve our equation below. So letter A, state this function's y-intercept. Where do we look to find a y-intercept? On the y-axis. So here's my y, well, if the line was straight, put him, there we go. We want to know, where does it intersect? You could write it as the y-intercept equals 1. Some of you might be used to b equals 1. Does anyone know the last way we could represent a y-intercept? Yes, ma'am, as a coordinate point. When x is 0, our y is 1. Great job. Between what two consecutive integers does the larger x-intercept lie? Where do we look to find x-intercepts? On the x-axis. So larger, is that going to be towards the left or towards, does that make sense? Towards the right? It's a weird word. I don't say that often. Left or right if we want the larger? Right. So between what two consecutive integers does that larger x-intercept lie? How do I draw the horizontal line y equals -2? Which way is horizontal? Uh-oh, we forgot. Which way is horizontal? Save the eye rolls for somebody else. Not me. Y equals -2. I want to bring letter D up here. Go away. Using our graphs, find the values of x that solve the equation below. We want to know when our function is equal to -2, what are those x values? When our function is equal to -2, what values of x solve that? Now, how do we do it algebraically? Frank? We typically do, but we have an x squared term. So we have to do something different when it's x squared.
Oh, do it with the 2 parentheses.
Yes, we have to factor him. When we factor, we have to be equal to something, though.
2.
Yes. So we're going to add 2 to both sides. Sophia, you're on fire today. We've got x squared minus 4x plus 3 equals 0, and then she said it's the 2 parentheses. So we're going back to factoring, everyone's favorite, factors of something that give us a sum or difference of something. If we're not familiar, factors of a times c. We look at our last coefficient to determine if it's a sum or difference. This is a sum problem, and we always want the sum of our b coefficient. What do we want factors of if it's a times c? We've got x squared minus 4x plus 3. Remembering it's ax squared plus bx plus c. What's our a coefficient? No. What's the invisible number in front of x squared? 1. What's our c coefficient? So we have 1 times 3. That gives us 3. What's our b coefficient? What do we want a sum of? 4. We never take the variable with us, just the coefficients. In the factor column, you list out the factors of 3, which are only 1 and 3. Sum means we add the 2 factors. 1 plus 3 is 4. Oh, and look, that's the number we need, so the pair we're going to use are 1 and 3. The final step is placing the signs. This S tells us to use the same signs. That's a trick. We look at the B coefficient to determine which sign to give them both. Beautiful. To solve for X, we tee it up. X minus 1 equals 0, x minus 3 equals 0, and we solve. And then you could even scroll up, go back to your function and look, hey, on that y equals negative 2 line, did we intersect the function at both x equals 1 and x equals 2? I'm sorry, at x equals 1 and x equals 3. And I don't want to scroll up because I don't want people to miss this, but yes, you see that we do intersect at those 2 points. Would this graph be a function? You guys all have the picture on your thing. Would this graph be a function? Yes or no? Yeah. It's a parabola. We do not have multiple values for any x value with our parabolas. What shape will never be a function?
Like a Z.
Okay, a Z. A circle. Circle is huge. There's another one. An ellipse. What were you going to say? A C. Okay, so a parabola that has been rotated, something like that. All right, so you can start getting familiar with, based off the looks and based off the equations, of whether something is going to be a function or not. All right, that's pretty much what I care about sharing with everybody at home. So let me stop this so it's not